Hello, and welcome to the video lecture for topic 23, the Diels Alder reaction. Now, the Diels Alder reaction is one of the most famous reactions in organic chemistry. It was discovered by Otto Diels and Kurt Alder, and it is a process for us to make six-membered rings. Fun fact, the Diels Alder reaction, Otto Diels and Kurt Alder won the Nobel Prize for their discovery of this reaction. They were awarded the Nobel Prize in 1950. They actually discovered it several years before that. So, in the Diels Alder reaction, what we have are two molecules, one called a diene, which we just saw in topic 22. So we have a diene, and we have another molecule with a pi bond in it known as a dienophile, a lover or seeker of dienes. So here's our diene, and this is known as our dienophile. This is a special reaction. It is a concerted pericyclic reaction, right? So concerted reaction, all bonds are broken and all bonds are made in a single step. It's known as a 4+2 cyclo addition. These are lots of little details, right, that you get more into in Chem 202. But suffice it to say that everything happens at once in this reaction. Our electron movement follows this pattern, the end result of which is that we form a six-membered ring. So if we notice what's happening here, we are breaking 3 pi bonds, and we are making 2 new sigma bonds and 1 new pi bond. So, right, I'm going to go ahead and number all of the atoms that are involved in this process so we can see where they end up in our products. So here's 1, 2, I'm going to call this 3, 4, 5, and 6. And so first thing I do is I'm breaking the pi bond between 1 and 2 and creating a sigma bond between 2 and 3. So here's 1 and 2, and I have created a sigma bond between 2 and 3. Now I'm breaking the sigma bond, the pi bond between 3 and 4. Excuse me, that's going to be atom 3. So I'm breaking the sigma bond between 3 and 4, pi bond between 3 and 4, and I'm making a pi bond between 4 and 5. Finally, I'm breaking the pi bond between 5 and 6, and I'm making a new sigma bond between 6 and 1. And so we have our diene and our dienophile, which react overall to give us a new six-membered ring, a new cyclohexene derivative. So this is the basics of the reaction. This is all the arrow pushing that you need to know. From here on out, we need to understand what is going on in this reaction to be able to determine a number of things. So we're going to take a look at the nature of the diene and the dienophile and how that ends up affecting the regiochemistry of how these two reactants align with each other to form our new product. We're also going to take a look at stereochemistry in both the diene and the dienophile and see how that is going to affect stereochemistry in the product. We're also going to take a look at the transition state, which is going to inform us a lot about how stereochemistry in the product is going to work out. So before we get into all that, I just want to give you a little bit to know. There is a lot that goes into the Diels Alder reaction. There's a number of different kinds of Diels Alder reactions. And this is a very, very broad topic that we just don't have the time to be able to get really in depth with. So what I'm going to show you are just the tip of the iceberg in terms of what there is to know about the Diels Alder reaction, and this is going to be sufficient for you in Chem 201 and in Chem 202. So as you progress through chemistry beyond your introductory OChem series, this reaction is going to come back to play a major role in a lot of the advanced synthesis and graduate level courses that you may take in the future. So To start off looking at the nature of the diene and the dienophile, my last comment on this is we are only going to look at what's called normal demand Diels Alder reactions, and that means that our diene is going to be electron rich, and our dienophile is going to be electron poor. So what do we mean when we say that our diene is electron rich? What we mean is that we are substituting our diene with some sort of an electron donating group. So we can do this in one of two ways. So here's a diene, and I can put an electron donating group, a methoxy, off of this terminal carbon. Arrow pushing to generate a resonance structure shows me that I can generate one resonance structure for this compound that puts a negative charge at that carbon, and then I can draw a second resonance structure that puts a negative charge at a terminal carbon. We can draw the resonance hybrid of it, but really what matters to us is this resonance structure here, where I've been able to put a negative charge at one of my terminal alkene carbons. Remember, on my diene, it's the end carbons that react with my dienophile. So I'm only interested in the resonance structures that will put a charge at my end carbons. Now, I could do a different type of substitution for my diene, where this time now I'm going to put my electron donating group internal. The end result is similar but slightly different. Here now I can only create one other resonance structure, where I'm able to put a negative charge onto that terminal, onto one of my terminal carbons. There's no way for me to push arrows here to get it down to this carbon at the bottom of my diene. So we see now how a electron donating group can give us what we can consider an electron-rich diene. A method by this electron donating group or this electron donating group gives me a method by which I can push electron density into one of my two terminal carbons of my diene. And we want our, our dienophile to be electron poor. So let's take a look at what that would be. So similar to how we used an electron donating group for our diene, we're going to want to use an electron withdrawing group for our dienophile. And these electron withdrawing groups are typically going to be something with a pi bond in them. So one example could be, I could use a carbonyl. I can't push down electron density out of my carbonyl, but I can push electron density up into it, drawing from my alkene. Again, I'm only interested in resonance forms that place some sort of a formal charge onto one of the carbons that are going to react in my dienophile, and so that's the carbons of the alkene. Here I can place a positive charge there. Another example would be a nitrile group. And again, while I can draw a number of, for this I can draw two other resonance structures, one of those resonance structures places the positive charge on the nitrile carbon. Now the nitrile carbon is just a substituent. It's not going to be participating in the Diels Alder reaction. It's not carbon 1 or 2. So the only resonance structure that really matters to me is the one where I can place a positive charge onto one of my alkene carbons. The third option that's pretty common is to use a nitro group. And again, I can draw resonance structures galore where I move electrons around between this nitrogen and two oxygens, but I'm only interested in the resonance structures that are going to actually affect my alkene that participates in my Diels Alder reaction. So this then becomes the resonance structure that truly matters to us. So again, we see here how an electron donating group can provide us with a resonance structure in our dienophile where we can place a positive charge onto one of those alkene carbons. It's very convenient that an electron donating group gives us the ability to place a negative charge on one of our diene carbons. So we're going to clear off the board and take a look at how this allows us to predict the orientation of how these two species will behave in a normal demand Diels Alder reaction. So we just saw how putting an electron donating group onto our diene and an electron withdrawing group onto our dienophile allows us to place negative or positive charges respectively onto one of the terminal carbons of either of those reactants. So what we can do is we can take a look at a couple of different scenarios. So let's say we have this diene with an electron donating group there, and I'm going to arbitrarily orient my dienophile so it has an electron withdrawing group as such. We could go through the exercise of pushing the arrows, but since I just did that, I'm just going to mark where our partial charges of interest are for us. Here we would have our delta minus on our diene, and here we would have our delta plus on our dienophile. Now, we want this delta minus to react with the carbon that has the delta plus. And so in this case, our dienophile is not properly oriented for the reaction to proceed. What we need to have is we need to have it oriented in the opposite way, such that now, if we orient it like such, we have our delta plus ready to react with our delta minus carbon. If we do our arrow pushing, and it really doesn't matter which direction we push the arrows, clockwise or counterclockwise, we see that ignoring stereochemistry, the new product we form would look like this. We form this type of a 1,2 product. Let's take a look at another example. Here now I'm going to put my electron donating group on my diene at a different position, and I'm going to this time use a nitrile on my electron withdrawing group on my dienophile. We can push our arrows, but since we just did that, I'm going to go ahead and tell you this is the diene carbon that carries the partial negative, and this is the dienophile carbon that carries the partial positive. Again, here our dienophile is oriented incorrectly. I could turn it around or I could turn my diene around. Dienophile takes a little bit less drawing, so that's the one that I'm going to reorient. So now our diene and dienophile are oriented properly based on charge to go ahead and react. And once again, it doesn't really make a difference which direction, clockwise or counterclockwise, that our arrows go, so long as they're all moving in the same direction. And this time we see that the substitution pattern we get in our product is a little bit different. And we're typically going to see that in a normal demand Diels Alder reaction, the scenarios that we've seen here, we're either going to get 1,2 products or 1,4 products, and we're never really going to see a 1,3 product forming from a Diels Alder a normal demand Diels Alder reaction. Okay, so up until now I have ignored stereochemistry. And stereochemistry is one of the more challenging aspects of the Diels Alder reaction. And so what we're going to do is I want to clear off the board and then come back and really walk through the different transition states and see how that affects the stereochemistry of the products that we can obtain. So I'm just going to use our first example from the last little part to take a look at these different potential transition states and see what's going on in them, since we have now our reactants aligned correctly, right, to determine how stereochemistry is going to work. This is a little bit of a complex topic. It may take a few times of watching the video to really get this down. Take your time with it. It will make sense. I will give little tips and tricks, little mnemonics that you can use to help you understand how the stereochemistry all works out. But really, it just takes a lot of practice with it, just like everything in organic chemistry does. I have drawn here our diene and our dienophile in the same plane. In reality, these two molecules do not exist in the same plane. When they react, if we imagine my papers here are the diene and my pen is the dienophile, they're going to need to approach each other in this fashion. Either the diene coming down onto, the dienophile coming down onto the diene, or the dienophile coming up to the diene. And so drawing this transition state, right, we're going to need to take a little bit of a perspective view on it. Right? There are some other things that we need to keep in mind, is that on our diene, we have 4 spots in these terminal positions. I'm going to call 2 of these locations out, and I'm going to call 2 of these locations in. These are on the outside of our diene. These are on the inside of our diene. So we need to keep that in mind. So I'm going to draw the first of 4 possible transition states, and then we're going to draw all of them out, and then I'm going to walk through each one. We're going to talk about what's going on in it and what the stereochemistry of the product in the end is going to look like. So, okay. So, the first possibility we have is we have here our diene. It's drawn very suggestive to suggest a certain orientation. We have our dienophile as such. We are going to make bonds in this fashion. Now, you can imagine that the carbonyl is away from the sigma bond. The carbonyl is on the opposite side of the sigma bond. That's one transition state. This is known, so this is a bottom attack transition state. The other transition state in this situation, we would have our dienophile approaching from the top, coming down onto our diene, again with our carbonyl away from the sigma bond. We can do a little bit of single bond rotation on our dienophile. We can create a slightly different bottom face approach, where now, by rotating around this sigma bond in my dienophile, I can place my carbonyl underneath that sigma bond, and again, we are forming bonds in that fashion. And then finally, I can have this same scenario. Can't forget my methoxy group there. I can have this same scenario, but now with a top face approach, my dienophile approaching my diene from a top face. Where we have, again, we've done that single bond rotation around here, right? And we've put this carbonyl group above the sigma bond of the diene. So these are the 4 possible transition states. Now, 2 of these are better than the other 2. And these are the 2 where we have the carbonyl, or the electron withdrawing group, situated either above or below the sigma bond of the dienophile. And what happens is that there is an interaction between this electron withdrawing group and the orbitals in this electron withdrawing group and the developing pi bond that's going to happen where our sigma bond in our dienophile is. And so there's this other attraction, this other interaction going on, right? And this is called a secondary orbital overlap. That helps to stabilize the transition state and further helps for that new pi bond to ultimately be created. Okay? And so because of this, we can now name these two different scenarios. One scenario where we have the electron withdrawing group away from the sigma bond, we call these, and that's true whether it's a bottom face or a top face approach, we call these exo transition states. And we have one where the carbonyl or electron withdrawing group of the dienophile is aligned with the sigma bond of the diene. We call these endo transition states. And the products that are derived from an endo transition state are known as endo products. The products derived from an exo transition state are known as exo products, right? Endo transition state is the favored transition state because it involves secondary orbital overlap. From there, we need to now form our new bonds and then see what the stereochemistry in the product is going to end up being. So, the exo transition state being less stable, we're not going to look at the products from that. We're strictly going to look at the products from the endo transition states. So I'm going to go ahead and erase these, and we're going to work out what these products are going to look like and develop some rules that are going to help us remember what in and out and how that's going to apply to stereochemistry in our products. Okay, so if we look back to our starting materials, we see that on my diene, I have a methoxy group out, and I have a hydrogen in at the carbon that has different substituents, whereas at this alkene carbon, this other terminal carbon, they're both hydrogens, really is not going to make a difference. So what we can remember is that for a bottom face approach, right, whatever is out will end up down, and whatever is in, so here now we have a hydrogen that's in, is going to end up. So when we form our bonds, so we're going to do all of our bond rearrangement, making and breaking, all ends up happening. And then what I'm going to do is, in my mind, I'm going to grab from the carbonyl and I'm going to open it up, right? I'm going to hold my diene part steady. I'm going to go flatten this out to see what my cyclohexane looks like. What I find, out goes to down. So here now is my methoxy group. In goes to up. My hydrogen would be up. And what happens in my dienophile is that the result of this secondary orbital overlap is going to, and this endo transition state, is going to put my carbonyl group on the same face of my cyclohexane that my out substituent was in. So here now I have my aldehyde group. If I do this same process here for my topside approach, what I'm going to find is out becomes down. That's going to hold true. But this time when I unfold, I'm going to grab my dienophile, whatever's on the bottom, and I'm going to unfold it into my diene, and I'm going to unfold it to be in plane with my dienophile. And so now what I get, again, what was out goes down, what was in goes up, right? That is still going to be on the same face as my out group. And if you look, these two transition states make for us a pair of enantiomers. So these two products are enantiomers of each other. All right, so that takes care of what there is to see in terms of stereochemistry arising from our, analyzing our transition states, seeing which ones are superior. We see that our endo transition state's superior, and we see that if we come from bring our dienophile top down onto our diene or bottom up into our diene, we end up with a pair of enantiomers. Again, this is best worked out with a model kit. Take your time with it. If you have any questions, please come and see me. It's a lot easier with help, but this is going to get you started. Sorrel does an okay job, but really doesn't get into the level of detail that I think is necessary for you to have. So the last thing that I'd like to talk about is stereochemistry of the dienophile and how that ends up being preserved in our product. Okay, so for looking at how the stereochemistry of our dienophile is preserved, I'd like to start off with just an unsubstituted diene. And we're going to take a dienophile and let's go ahead and make a trans dienophile. Now, what happens when this reaction proceeds is that, again, we're going to approach from a single face. We're going to find that endo transition state. We're going to approach from the right face. And so what we'll see in our product is that if we have a trans or E alkene as our dienophile, that stereochemistry will be preserved, and that we will end up with the trans relationship in our cyclohexene that we form. And we're going to make, because we know we can go from top face or bottom face, we're going to make this compound plus its enantiomer right? So these become the two options. Similarly, when we begin unsubstituted diene, here now I'm going to start with a cis dienophile, or a Z dienophile, if you will. We end up having that stereochemistry preserved, where the two substituents on my dienophile end up, let's make that a little bit more clear, excuse me. These two substituents from my dienophile end up on the same face of my cyclohexene, plus we know that we will also make the enantiomer. All right, so that basically wraps it up for what I need you to know, or what I expect you to know for the Diels Alder reaction. Getting a handle on the transition states, getting a handle on the stereochemistry coming from the diene, right, is going to be a little bit of a challenge. Definitely encourage you to bring any questions you have to lecture, conference, office hours, or make an appointment to see me one-on-one. And as always, thank you for watching.